Greetings everyone. So in this video we are going to discuss about a new topic, alkyl halides. Now, as we have done previously, the benzenes, it has been in which we discussed about several mechanisms, several reactions through which benzene reacts. Likewise, we got certain mechanisms in alkyl halides which kind of resemble to benzene as well. So let's just look into those as well. So first, let's understand what is alkyl halide. Whenever we are going to have an alkyl group, we are going to have an alkyl group which is attached to a halogen atom. Then at that point, it is known as an alkyl halide or halogen alkane or halogenoalkane, haloalkane, whatever we call it. Alright. So when we take this part, this is the alkyl chain. This is a non-polar part, and this is the halogen or halide group, which is polar. Now we just look into um, some general characteristics. The alkyl group, let's say if I draw an alkyl halide over here, this is example of an alkyl halide. So over here, this alkyl halide is having a carbon attached to the chloride. Now this carbon which is present over here is having hybridization of sp3. It is having sp3 hybridized orbitals, which is having of course a tetrahedral shape and 109.5 bond angle. If I were to make it pretty clear like this, and chlorine's p orbital like this, and in that way let me just draw a few more orbitals. This is that way, this is that way, this is that way, and here we go with um, the oops. This is not going to be an s orbital. This is going to be this one orbital, sp3 orbital, sp3 orbital, sp3 orbital, sp3 orbital. So this is basically the structure. It's a bit tardy, but that's the structure actually. I just understand from some physical properties. Physical properties is such that it is a highly reactive group. It is a reactive group. It is a reactive hydrocarbon, and that is soluble in water. They have a soluble. They are soluble in water, but their solubility decreases with the increase in number of carbon atoms. What actually happens is when we increase the number of carbon atoms, the non-polarity is overpowered by the polar segment, due to which the non-polarity overcomes the polar segment, and that causes to make the higher alkyl halides to become non-polar in nature essentially, and ultimately make it less soluble in water. So let's just move on to its reactivity. When we discuss reactivity of alkyl halide, we consider two factors. Number one is bond energy. When we just understand the concept of bond energy, it is the energy that is required to break or form a bond, um, and that basically um, is in such a manner that if you just let's say consider, if I consider alkyl fluoride for example. Fluorine is the most electronegative halogen, and that being most electronegative draws the electron cloud, draws the electron cloud of carbon towards itself. I'm just trying to draw the electron cloud. It draws the electron cloud towards itself, such that if this is electron cloud, then that electron cloud is drawn towards fluorine the most. Fluorine has the electron cloud entirely. I mean, like not entirely, but to the most extent, and that basically makes fluorine to form that causes fluorine to form a very strong bond with carbon. And due to this reason it is having a high bond energy. It is having a high bond energy. Now if you just compare it with its counterpart, alkyl iodide. Alkyl iodide is having the least electronegativity in halogens, so it is going to make essentially a weaker bond with carbon, which means it is having the least bond energy. Least bond energy, which is essentially because it has a weaker bond, which means it is easier to break that bond, so less energy is required. So least bond energy in carbon iodide, and for alkyl fluoride, the highest amount of bond energy is required to break the bond. So because the bond is pretty strong, that's why it is having the high bond energy. So if you just compare the reactivity on the basis of bond energy, we will find that alkyl iodide having the weakest bond are the most reactive. Then we have alkyl bromide. Then we have alkyl chloride. Then we have alkyl iodide. So this is the sequence. After that, we have another factor to be considered: electronegativity difference. So electronegativity difference. Electronegativity difference is found to be highest between carbon and fluorine, due to which carbon and fluorine's bond makes fluorine the most negative and carbon the most partially positive, and fluorine the most partially negative. And due to this reason, fluorine becomes a strong nucleophile. And due to this reason, it is easier for any electrophile to come to fluorine. It is easier for any electrophile to come to fluorine and attack it and replace it. So sorry, it can any electrophile can come and basically attack the carbon and replace it, or any other nucleophile can come and easily attack it and break it. So because of this reason, we have the reactivity according to electronegativity difference as this. If we just consider the for attack of electrophile. If there is an attack of electrophile, then this reactivity sequence would be considered: fluorine greater than chlorine greater than bromine, and then we have iodine. But if we just look into the overall reactivity, usually we do not have electrophilic reactions with alkyl halides. Usually we do not have electrophilic reactions with alkyl halides, due to which when we consider overall that what should be the reactivity of alkyl halides, we consider this, because uh, this condition is valid for nucleophilic reactions, and for electrophilic reactions, electronegativity different accounts. So usually electrophilic reactions are not done by alkyl halides, so we do not consider that. So that's about it. Let's move on to the next part, which is preparations. um, it can be prepared from alcohols in many different ways. Number one way is when we are going to react it with zinc chloride in the presence of HCl. When you are going to react an alcohol zinc chloride in the presence of HCl, then it's essentially going to produce the ethyl chloride or any other ethyl halide which is present as the hydrogen halide. And then we have the reaction of alcohol with thionyl chloride in the presence of pyridine solvent, due to which we have formation of sulfur dioxide, HCl and ethyl halide. Now, if you just take the form in which both sulfur dioxide, oops, the form in which both sulfur dioxide and HCl are found, both of them are found in vapor form, due to which this method is highly preferred because it's easier to extract the ethyl halide. And then we have uh, the phosphorus trihalide, phosphorus pentahalide, which react with alcohol to produce the alkyl halides. And then we have alkanes. We have already studied it as well. That whenever we are going to perform, whenever we are going to perform dehalogenation of alkanes, whenever we are going to perform halogenation of alkanes with the help of free radical substitution, when we are going to perform free radical substitution, halogenation of alkanes, then at that point we are going to get um, alkyl halides. But the problem with free radical substitution is that free radical substitution can sometimes become overpowered, and alongside alkyl halides we can get di-substituted alkyl halides as well. Instead of monohaloalkanes, we sometimes get dihaloalkane, trihaloalkane, tetrahaloalkane. So that can be a problem as well, such that there is uh, no guarantee that 100% pure alkyl halide will be found. And second, this one is pretty important because that's important to obtain alkyl iodide. Basically, alkyl iodide is not obtained easily with the help of free radical substitution. Uh, Alkyl iodide is let me just explain you in a pretty simple way. The human body needs iodine. The human body needs iodine. Why does it need iodine? It needs iodine for proper growth and metabolism. So it is highly recommended by doctors and pharmaceuticals to take iodine in their diet. So whenever we are taking iodine in our diet, it's crucial for us to have iodine enter our cells. Sometimes whenever we are having iodine, it is crucial for that to enter our cells, body cells. But the problem is the body cells are having a cell membrane which is non-polar, and that non-polar cell membrane does not allow the polar iodine, because iodine is a halogen, it's electronegative, so it's polar, does not allow iodine to come inside the cell. So for that, what we actually do is we actually attach an alkyl chain to iodine in order to allow the alkyl iodide to get inside the cell and perform all the metabolic or growth functions in body. So that's the reason we need alkyl iodide on an industrial level for making iodized salts and other purposes. For that, we cannot use free radical substitution, because in free radical substitution iodine does not react at ordinary conditions. And for that, what we do is we basically take an alkyl chloride or alkyl bromide chain, and then we react it with sodium iodide, and that basically forms alkyl iodide. That's basically a very famous reaction named as substitution. It's kind of a substitution reaction, because one nucleophile is replaced by another nucleophile. Now let's just move on to reactions. What sort of reactions are there? Uh, there are generally two major types of reactions which are present. Two reactions which are present. Number one is the nucleophilic substitution reaction. Nucleophilic substitution reaction. And the second reaction is elimination reaction, which is also known as beta elimination reaction. This is SN reaction. It is also known as SN reaction, and that is also known as beta elimination reaction. So let's just understand what actually happens in these reactions. Nucleophilic substitution reaction is the one in which, let's say, if this is the alkyl halide, this is the nucleophilic part. This alkyl halide is partially negative, so it is a nucleophilic part, and this is partial carbon, which is partially positive. That is the electrophile. So what actually happens is that whenever there is an attack of a nucleophile, whenever there is an attack of a nucleophile, then at that point, that nucleophile causes to replace alkyl halide and forms a substituted product which is known as the nucleophilic substitution reaction. An elimination reaction is the process in which the hydrogen iodide, sorry, not hydrogen iodide essentially, but hydrogen halide is removed. It is removed or eliminated from alkyl halide. So this is the basic concept. Let's just understand it in a very better way. So basically, SN1 and SN2 mechanism, SN reactions. SN reactions are divided into two major categories. There are two different pathways from which SN reactions can happen. It can either go through the SN1 mechanism, or it can go through the SN2 mechanism. So the very basic difference between these reactions, SN1 and SN2 mechanisms, is that uh, very basic difference between SN1 and SN2 is that SN1 mechanism is a unimolecular two-step reaction. It is a two-step reaction. It is a unimolecular reaction. It happens in tertiary alkyl halides. I mean, like, that's something we can consider at the end as well. Tertiary alkyl halides, and it is a first-order reaction, follows first-order kinetics. While if you talk about SN2 mechanism, it's a bimolecular reaction, and that is one-step reaction. And that usually happens in primary alkyl halides. Let's just understand what it is. Before understanding these mechanisms, we just need to have a good understanding of some basic terminologies that need to be understood. So let's just understand those. All right. So basically, whenever there are certain terms used in this uh, chapter, in using this process. Number one is substrate. Substrate. What is a substrate? Substrate basically is a reacting molecule, which is essentially coming and in which the actual reaction is happening. So substrate over here is alkyl halide. Second component is the nucleophile. So the nucleophile basically is the negatively charged uh, species which is attached to the substrate, and that is responsible for being replaced. Sorry. Basically, nucleophile is the incoming agent is the incoming agent that attacks over the substrate and replaces the this group. It replaces this group. So nucleophile can be of various things. It can be negatively charged or neutral as well. So uh, in this reaction, we do not have such preference that we need a strong or weak nucleophile. Even if it is a neutral or weak nucleophile, it can work. And then we have leaving groups. Leaving groups. So what is a leaving group? Leaving group basically, let's say if I draw alkyl halide. Now in this, if you just see this halogen, this is a leaving group, which will be leaving the alkyl halide during nucleophilic substitution reaction, that is known as a leaving group. Now, it is important that the leaving group should be always weaker. Leaving group and nucleophile. Nucleophile is always supposed to be stronger. The incoming nucleophile is always supposed to be stronger than the leaving group. This is an important point. Now there are some leaving groups which are bad, some leaving groups which are good. If we talk about good leaving groups are those which form are those leaving groups which form weak bond with carbon. And what are those leaving groups which form weak bond with carbon? Those are with low electronegativity value. And what does it mean? This means that those atoms which are having low electronegativity value form weak bond with carbon, and they can be considered as good leaving groups. And if you just talk about some examples, that is iodide, because essentially the leaving groups are in charge form, because when we leave, they do not leave in the form of a neutral atom or a free radical. They leave in the form of a negatively charged nucleophile. So iodide, chloride, HSO4, all of these are good leaving groups. Why? Because they have a large size. Because they have a large size, due to which they have a low electronegativity value, due to which they have a weaker bond with carbon, due to which they are good leaving groups. While if you just talk about the small sized atoms or small sized ions, they are having high electronegativity, and because of high electronegativity value, they form a strong bond with carbon, and they do not leave easily carbon. They do not leave carbon very easily. So for that purpose, we call them as bad leaving groups. Example of bad leaving groups include OH. It includes oops. It includes OH. It includes acyl group. It includes nitro group. These are bad leaving groups. So these are some important points to be understood. Alright. Now let's just move on to the mechanism. So what does the mechanism sound like? If you were to draw the mechanism very conceptually, first if you just draw the um, SN1 mechanism is quite easy. It's just got two steps. Number one is step in which there is formation of a carbocation. What actually happens is the nucleophile and the nucleophile in alkyl halide, the nucleophile or the leaving group leaves the carbon and forms a carbocation, and in the second stage that carbocation is attacked by a nucleophile, the incoming nucleophile, and that incoming nucleophile then attaches, due to which the bond forms. The first step is pretty slow because that's the rate determining step. It is in equilibrium as well. It is in equilibrium, it is a reversible step, and it is a rate determining step of the slow step. Because in this there is breakdown of covalent bond. And in the second stage is pretty fast, and it is the irreversible stage. Why? Because in this stage there is formation of reaction of ions. So these are the two important things to be understood. And there is another important thing that I would like to mention over here, which is that SN2 mechanism goes on. SN1 mechanism, sorry, SN1 mechanism is preferred in a polar solvent. It is done in a polar solvent because in polar solvent it is done in a polar solvent because in a polar solvent uh, the carbocation which is formed becomes the carbocation which is formed becomes more unstable, and the reaction is pretty fast. Now, polar solvent which you are going to utilize in an SN1 mechanism should not be water. What? Because of course we cannot dissolve an organic compound in water, but that should be an organic polar solvent. It can be acetone, it can be ethyl alcohol, organic polar solvents. These are the solvents in which it is dissolved. And another important point about this is that here carbocations are sp2 hybridized. What actually happens is when if you just see this diagram, oops, you just see this diagram at first stage. This is alkyl halide. It's a tertiary alkyl halide. When what actually happens is the chlorine atom leaves the alkyl group, and that forms carbocation and chloride. Now that carbocation basically alkyl halide over here was in sp3 hybridized form, but the carbocation is in sp2 hybridized form. It is tetrahedral, a 3D structure, and this one is a planar structure, trigonal planar structure, which is a 2D structure. So why does it happen? Because sp2 hybridized orbital has a planar structure, and that planar structure provides more area to the nucleophile to come and it, attack the carbocation. But in tetrahedral structure, it becomes really difficult for chloride or any other nucleophile to come to the carbocation and the attack the carbocation, because in 3D structure there are three dimensions involved, and literally it can the carbocation can be attacked from anywhere. So in that way, this is about it. Now once the sp2 hybridized orbital is formed, that sp2 hybridized orbital of carbocation, when carbocation reacts in the second stage with the incoming nucleophile, that forms the product, and that product again becomes sp3 hybridized. So this is the reaction. Now if you just look into a bit detail of this, we need to understand that there are different carbocations. Different carbocations. There is a tertiary carbocation, there is secondary carbocation, primary carbocation, and there is methyl carbocation. Let's just understand these. If I were to draw their structures, it would be like this. It would be like this. Carbon, um, CH3, CH3, CH3. This is the structure. Let me just try to draw, try to make it a bit small. Let's draw another one more, and one more. All right. So now let me just make a few changes to these. In secondary one, let's just remove one more. Let's just remove this H, and let's just remove some here. Um, H, H, and then I should remove this one as well. I should remove the halide group because basically it's a carbocation. It's an unstable species, right? So I'm not going to draw the cation. I'm not going to draw the halide over here. Here's a positive charge, and this is about it. Hydrogen, hydrogen. All right. So our structures look perfect right now, and now let's just understand this. So if you just look into this, look into the first structure. This is the tertiary carbocation because it is having one carbon which is attached to three other carbon groups. So in that way, it is a tertiary carbocation, and that tertiary carbocation has two major things to understand. That whenever we are going to have an SN1 mechanism, then an SN1 mechanism is going to prefer tertiary carbocation. All types of nucleophilic substitution reaction can follow SN1 mechanism, SN2 mechanism. For example, we can do use primary alkyl halides for SN1 mechanism. We can use secondary alkyl halides for SN1 mechanism, and we can utilize tertiary alkyl halides for SN1 mechanism as well. But SN1 mechanism usually prefers tertiary carbocation, tertiary alkyl halides. Why is that so? The reason behind it is that there are basically two reasons. Two reasons are there. Number one reason that I'm going to write over here. Number one reason which I'm going to write over here is the inductive effect. Inductive effect. And the second reason is stability of tertiary carbocation. What does it mean? Let's just understand. If you see the inductive effect, you just see the structure of this carbocation, you will actually find a few things that over here. you just look over here, you will actually find this thing that this carbon which is present in the center, it is actually having three groups attached to it: CH3, CH3, CH3. There are three groups attached to it. So, are we actually going to have impact of these groups on the central carbon? The answer is yes. The central carbon is going to be affected by these groups. What actually these groups do is these groups donate their electrons, donate electrons to the central carbon. They donate the electron to the central carbon, right? They basically donate the electron to the central carbon, due to which the central carbon becomes less positive. Its positivity decreases. It gives its electron to the central carbon, this one gives its electron to the central carbon, and that becomes less positive. It does not become entirely negative, but becomes less positive because of more electrons being, more of the electron cloud density being towards the carbon. Um, Basically, it does not gives the electron, does not donate the electron pair, but makes the electron cloud um, nearer to the central carbon, due to which there is less positivity. And because of this less positivity, the nucleophile which is attached to it, for example, let's say if it is the, let's say if we are is having let's say if we are having uh, fluorine attached over here, then that nucleophile would not be making a really strong bond with carbon, which is having less positivity. It needs a carbon which has more positivity to make a stronger nuclear, to make a stronger um, chemical bond. And for that purpose, this inductive effect, this effect of the bulky groups which donate their electron to this, makes the central carbon unstable, and that basically makes it capable of the makes it capable of leaving the leaving group, leaving the leaving group very easily. And thus, because it leaves a leaving group pretty easily, it can form, leaving group pretty easily, it can form an SN1 mechanism very nicely. It can easily form an SN1 mechanism. So this is one point that needs to be considered. Second point that I really want you to understand is stability of the tertiary carbocation. The tertiary carbocation, if you just look into the tertiary carbocation, it is a stable molecule. It is a stable molecule. Why do we call it a stable molecule? Basically, the reason we call it a stable molecule is that it is having few things. It is a stable molecule. It's a very stable molecule, right? It's a stable carbocation. It's a stability, or there's stability in this carbocation, because let's say if we are having, I'm having a nucleophile. Let me choose a nuclear. Alright. So let's say if I'm having a nucleophile. This nucleophile comes and that attacks over the carbocation. So can you just tell what, from what sides can the nucleophile can attack? If nucleophile cannot certainly attack here, because there are these bulky groups which uh, produce steric hindrance. Due to steric hindrance, basically is the presence of bulky groups which prevent the attack of any nucleophile or electrophile on the central carbon. So that is known as steric hindrance or steric effect. And because of the steric effect, a nucleophile cannot attack from here. It 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 can not even attack from here. It can only attack from here. From here. So the point to understand is whenever we are going to have a tertiary carbocation, it has more bulky groups, which make it less reactive due to steric hindrance, which generates steric hindrance, and that causes the reactivity of central carbon to decrease because nucleophile, the excess of nucleophile to the carbon to the central carbon, or we also call central carbon as alpha carbon, in which the reactivity of central carbon or alpha carbon, the nucleophile cannot attach to the alpha carbon, and the basically the sites of attachment of nucleophile to alpha carbon is limited, due to which alpha carbon becomes less reactive, and that's the reason that it makes it. That's the reason. That's the reason. The tertiary uh, carbocation is more stable. So, why did I tell you such a long story? Tertiary carbocation has a steric effect, and because of the steric effect, the incoming nucleophile cannot attack, uh, cannot, because of the steric effect, it uh, can attack from the central side, it can attack from front, as well as it can attack from the back. But if you just take primary alcohol, not primary alcohol, primary alkyl halide, if the same nucleophile is attacking the primary uh, carbocation, then it's going to attack from here, from here, from here. But which essentially makes the tertiary carbocation more suitable for attack for both front side and back side, due to which it produces a racemic mixture. It produces a racemic mixture, a mixture in which there is 50% inverted configuration and 50% retention configuration. But it actually also depends on the nucleophile which is used. Basically, when we are going to use a strong nucleophile, then at that point the ratio of inversion configuration is increased. So this is a point that need to be considered. And strength of carbocation, as I previously told, is this. Stability is this. Tertiary carbocation is the most stable one, and then we have the secondary carbocation and the primary, and then the third carbocation, which is the most stable. So this is all about SN1 mechanism. SN2 mechanism is pretty simple. In SN1 mechanism, we had an intermediate, which is carbocation. But in SN2 mechanism, we do not have any intermediate. We just have a single step reaction, which has a second order reactivity. So basically, in this reaction, what actually happens is um, OH group comes, any sort of nucleophile comes, it does not attack from the front, because on the front we are having bromine, which cannot allow the attack on carbon. From the back, so it attacks over the back. It comes from the back and attacks from the back on the carbon, so that it can actually attack on carbon and form the nucleophile. So how the reaction proceeds is that it's a single step reaction, but for the sake of easiness, we are going to divide it into few steps. Heterolytic fission, it's a heterolytic, first heterolytic fission happens, due to which this carbocation formed and there is formation of bromide. There's actually no formation of carbocation, but what actually happens is first heterolytic fission happens, and then there is formation, and then there is attack of the nucleophile, and then there is formation of transition state, or also known as activated complex, Transition state and activated complex are not the same. Transition state, activated complex are the same thing, but transition state and intermediate state are different things, because intermediate state basically can exist in a real world for a lot period of time, but transition state only exists for fraction of milliseconds. So it's an important point to consider. And formation of transition state, and there is another important thing which is balancing. What actually happens is, what happens is that we are having and we are having an alkyl halide. What actually happens is that first there's formation of this first there is heterolytic fusion, due to which there is partial charges present on the alkyl and bromide, and then the nucleophile attacks, and that basically forms a transition state, this activated complex. And then what actually happens is, from the activated complex, the leaving group is taken out, and then that and the rest of the molecule then rearranges itself to form the inverted molecule. In this type of reaction, the ratio of inverted molecule is 100%. There is no retention configuration. 100% inversion configuration is there. So that's all about this reaction, and that is favored in non-polar solvent, because the reaction is so violent. It is only favored in non-polar solvent. And now another important thing, that primary alkyl halides prefer SN2 mechanism, and tertiary alkyl halide prefer SN1 mechanism. Why is that so? Because primary alkyl halides do not have any steric entrance, due to which the due to which the nucleophile can easily attack in case of primary alkyl halide. But in tertiary alkyl halide, there is a steric hindrance which makes it pretty difficult. And that makes it more suitable for SN1 mechanism, because in SN1 mechanism the reaction occurs in two steps. So in that way, the tertiary alkyl halide, because of having steric hindrance, needs to make a carbocation first and then attack the nucleophile, due to which the two-step mechanism of SN1 reaction makes tertiary alkyl halide a more suitable choice than primary alkyl halide. Let's just move on to the next one. Alright, these are the questions. These are the topics covered. Now let's just move on to E1 and E2 reactions, or the elimination reactions. Elimination reactions are not that difficult at all. So if you just look into the elimination reactions, elimination means when you are removing hydrogen halide from hydrogen halide from the alkyl halide. So when you're going to remove hydrogen halide, that actually happens in such a way that uh, it again takes place in two mechanisms, E1 mechanism and E2 mechanism. E1 mechanism is in such a manner that again it's going to be a unimolecular reaction. It's going to be a two-step reaction like SN1 mechanism, and that's going to be preferred by a tertiary carbocation. A tertiary carbocation which is having a beta hydrogen. Now, if you just look into this compound, let's say if I'm having this compound, this is having this central carbon. The central carbon is known as alpha carbon, or the reaction center. The carbon which is attached adjacent to the alpha carbon is known as the beta carbon. And the good thing about beta carbon is that beta carbon donates its electron towards this due to inductive effect. And let me just make the structure pretty clearer so that it becomes easier to understand. This is let's say the beta carbon, this is hydrogen, this is hydrogen, this is hydrogen, this is hydrogen, this is the entire molecule, right? This is the entire way. Now, if you just see over here, um, the beta carbon will donate its electron. Oops, let me just draw a few more things in it. One chain here. Alright, so if you just look into this, we will basically understand the fact. If you just look into this, we will understand the fact that this carbon donates its electron to the central carbon, alpha carbon. This carbon will give its electron to this. This carbon will give its electron to this. Due to which this carbon will become less positive. It will become more negative and less positive, and these three carbons will become more positive, more positive, more positive. But there is a problem. These hydrogen atoms which are present on the side, these also undergo an inductive effect. They also cause an inductive effect over these carbons. They also cause an inductive effect. How do they cause an inductive effect? Let's just understand this. Let's just understand how do they cause an inductive effect. So the inductive effect works in that manner, like this is a hydrogen. That hydrogen, gives its electron pair to it. This hydrogen gives its electron pair to it, and this hydrogen gives its electron pair to it. Due to which the beta carbon becomes partially negative, just like it becomes more negative, less positive, and this becomes more positive. This becomes more positive. This becomes more positive. And due to this reason, this beta hydrogen can then be easily attacked by a nucleophile. And by the way, what type of nucleophile is used? The nucleophile which is used is a base. A strong base is used as a nucleophile, which is smaller in size, because smaller size bases are strong bases which can actually attract the partially positive hydrogen towards it to create to undergo the substitution reaction pretty easily. So this is some basic principle we need to understand. We just take even reaction. Even reaction is again favored in a polar solvent, and that the first step is slow, in a reversible step, rate determining step, in which carbocation is formed and bromide ion is formed, and then that carbocation bromide ion is at OH comes from the back side and attacks with the beta hydrogen, and that basically causes to form, and that basically causes to eliminate. Oops, causes to attach with a beta hydrogen and forms water molecule, and then the in the second step there is formation of an alkene as a result of the reaction. This is about even reaction. If you just talk about E2 reaction, E2 reaction proceeds in such a manner that in an E2 reaction there is a direct formation of a transition state, and from the transition state there would be the formation of an alkene and then a bromide and then a hydrogen, uh, and then an H2O bond. So this is how the entire reaction works. Um, if you just look into both of these reactions, if you just look into both of these reactions, we will find that this does not require a non-polar solvent. This requires a polar solvent. And again, these are having pretty similar to the even and SN1, SN1 and SN2 reactions. This is also the biomolecular single step reaction, and that's also having first order kinetics, and these are the important things for understanding. And then we are having some further some other reactions for alkyl halides, such that whenever we are going to take alkyl halides and react it with sodium in the presence of ether, it's going to produce a symmetrical alkane. A symmetrical alkane. And that symmetrical alkane is pretty useful for industrial purposes. And that was given by a word scientist named as word synthesis. And then we have dehalogenation. Dehalogenation is a process which we studied previously as well, in which we take zinc in the presence of an aqueous acid, and we basically convert alkyl halide into alkane. And then we have another reaction, which is the reaction of sodium lead alloy with alkyl halide. Such that when sodium lead reacts with alkyl halide, then it basically forms the tetramethyl lead. If it is reacting with methyl chloride, or you know if it is reacting with tetramethylene, when reacting with methyl halide, when it is reacting with ethyl halide, it's going to form tetraethyl. Both of these are used as anti-knocking agents in gas solid formation. So these are used as anti-knocking agents. This is important. Now let's just make a quick comparison of substitution and elimination reaction. Because whenever we are going to have the reaction of alkyl halides with a nucleophile or a strong base, what actually happens is it's not possible that substitution and elimination reaction occur separately. These reactions do not occur separately. These reactions do not occur separately. These reactions basically, whenever we are going to add a nucleophile to an alkyl halide, some of the molecules will undergo the substitution reaction. Some of them will undergo elimination reaction, and some will undergo substitution, some will undergo elimination reaction, and they will compete with each other to form a particular type of reaction. Whenever we are going to have a beta hydrogen in an alkyl group, whenever we are going to have beta hydrogen or a beta carbon in an alkyl halide, then it basically favors the elimination reaction. But if we are having alpha carbon, which is of course essential, if there's alpha carbon, then it's going to favor substitution reaction, nucleophilic substitution reaction. By the way, there is electrophilic substitution reaction as well that only occurs in alcohol. We are going to study that as well. Alright. So let's just understand some factors on which we can increase the yield of substitution reaction or the elimination reaction. So number one factor that needs to be considered is the substrate. Whenever we are going to have a tertiary alkyl halide will favor elimination, because tertiary alkyl halide can easily has a lot of steric effect, has a lot of inductive effect, which makes the beta hydrogen readily available for the base to come and attack and eliminate the beta hydrogen. So tertiary alkyl halide will favor elimination, and primary alkyl halide will favor substitution. Second point which needs to be considered is the nucleophile. So the incoming nucleophile, if the incoming nucleophile is a strong base, if it is a strong base, then it's going to favor elimination. We have understood that whenever we are going to have a strong base, then it has more electronegativity, which can actually have more power to attract the beta hydrogen towards itself. And weak base will have substitution reaction. Another important point is the solvent which is used. So basically, whenever we are going to compare elimination with substitution, the polar solvent will favor substitution, and non-polar solvent favors elimination. Then another important factor is leaving group. Leaving group essentially does not make a big difference. In both of the biomolecular steps, leaving groups do not make a difference. But if we talk about leaving groups in terms of unimolecular reactions, then good leaving groups are essentially required for healthier reaction in both unimolecular cases. In unimolecular cases of both reaction, cases of SN and elimination reaction, leaving groups should be good. Good leaving groups preferred. Another important thing which needs to be considered is the temperature. Temperature plays an important role as well. Whenever we are going to have a high temperature, then that is going to favor the elimination reaction. High temperature is going to favor the elimination reaction, because when high temperature is there, it is easier for the beta hydrogen to be separated from the beta carbon and thus combine with the nucleophile. But if you're having low temperature, then it's going to make it much more difficult, and rather it's going to favor substitution reaction. Substitution reaction is already pretty unstable, so it's going to prefer substitution reaction. So high temperature, elimination reaction, low temperature reaction, low temperature, substitution reaction. These are certain factors needed to be considered. Alright, so that's all about this video. In this video, we have actually covered in detail all the important points about the alkyl halides, and hopefully in the next video we're going to discuss the Grignard's reagents and the amines. So if you have any comments or have any questions, so feel free to reach out and comment down in the chat box. Thank you.